Okay, so we're going to learn about friction and its relationship to the normal force. So, friction and the normal force. So, last class we studied the concept of apparent weight, okay? And we realized that weight as we feel it is actually really the normal force pushing back up on our body. Just to reiterate that, imagine that we have a scale on some springs, okay, and a person is standing on the scale, right? We talked about how if you accelerate up, the scale reads heavier. If you accelerate down, it reads lighter, and so on. But now what we're going to talk about is the relationship between this upward normal force and how easy or difficult it is to cause something to slide right or left. Okay? So this, resistance to sliding is called friction. And it is related to the normal force. Oops, that's not how you spell resistance. Resistance to sliding is called friction. Okay? It is related to the normal force. Okay. Oh dear. What just happened? What is happening? Why is that doing that? Something super weird just happened. Okay, so in order to understand friction a little bit better, we're going to do some imagining here. So, let's imagine that we have a nice block here, and this block is sitting on the ground. Okay. Heavy ground. Get it like this color. There we go. Okay. So this is going to have some weight to it, right? It's going to have a mass, first of all. Let's make it 100 kgs. Okay? And there's going to be a downward force acting on this guy. So let's draw that in. There it is. We had a name for that, right? What do we call the downward force that gravity causes? Yeah, we could call it Fg, and that's equal to mg. It's also called weight. It means the same thing, right? We know that. And we also see that this is sitting on a surface, so there's a reactionary force to gravity pointing in the upward direction, and we call that the normal force. Normal force. Okay? And in the vertical plane, if there's no acceleration in the vertical plane, then weight and normal force would be exactly equal. Need this. So Fn is essentially equal and opposite to mg, right? It's the upward version of weight, okay? So the net force in the y-plane, in the vertical plane, is 0. Okay, so now what we are interested in here is the amount of pushing force required to get this thing to move, okay? And so if you are attempting to push on this, right, you would likely experience resistance to that pushing, okay? And that is what we call the force of friction, okay? Force of friction. So let's talk about this scenario. So if this were to, like let's imagine this is sitting in an elevator, and if the elevator were to accelerate downward, okay, well, the normal force would decrease, okay? Normal force would decrease, and in fact, if the elevator went into free fall, the normal force would drop to nothing, and everything would just be floating around. But as the elevator increases its downward acceleration, friction gets lower and lower and lower, right? This gets easier to slide left and right with that lower friction. Realize we have not done anything to the weight. The weight is still the same. What we have changed is the normal force. if this goes into a acceleration upward, a very high acceleration upward, like imagine movies you've seen where people are taking off in a rocket and they're just like mashed to their seats. Well, now imagine trying to slide something that's under those conditions. It would be very difficult. So what this tells us is that this is the key to understanding friction. The higher the normal force, the more difficult it is to make this thing go. Or in other words, the larger the frictional force. So there's a relationship between those two things. And there's one more important factor to think about when we're talking about friction. And that is the nature of the materials. Okay? So these materials, depending on what they are, will change the amount of friction. So for instance, if this is a block of ice, if this is ice, and this is like, I don't know, something really smooth, like a waxed toboggan, friction would be like very low. It would be super easy to slide this around on the ice. Conversely, if this is made of like rubber and this is made of rubber, okay, the friction would be very high and it'd be very difficult to slide back and forth. So that's the second thing that's important. So friction relies on two things. Let's just define them or say what they are. So friction is dependent on two things. One, the normal force. And two, mu, which is called the coefficient of friction, and is based on the nature of the materials. So it's different for every two surfaces, okay? So I'll put it was unique for any two surfaces. Okay, so how do we use this information? So let me just make another note of this. Okay, so this mu value here, right? This mu value essentially it's called a coefficient and it has no units. All it does is it relates normal force to frictional force. Okay, so another way to think about this is this: the force of friction is going to be proportional to the normal force. Okay. And to find an actual value for it, we need to use that coefficient, which is specific to a particular condition. Maybe it's ice in a toboggan, or maybe it's your shoe and the floor, or maybe it's like a box and the tabletop, or something like that. They're all going to have their own mu values, okay, but you're going to get this relationship. So one other way to look at that, if you want, is if you want to find a mu value is going to be equal to the normal force ratio to friction. Okay, how much normal force or how much friction you get for a given amount of normal force essentially is how that's going to look. Oops, sorry, I did that backwards, didn't I? My mistake. Let me just fix that. How much friction you get for a given amount of normal force. That's better. That's how that should look. Okay? So we'll do a quick example. It's pretty easy. A 10 kilogram mass is pushed along a table with a force of 10 newtons. It travels at constant velocity. Find mu. Okay, so let's solve this guy. Okay, so we'll put a block on the table. There it is. Should be a different color, I think. Perfect. All right, so some things to remember. This is a 10 kilogram mass. We're interested in the weight here, right? So Fw equals mg. So we get 10 kgs times 9.8 meters per second squared. So you get 98 newtons. That must mean, in this case, we have normal force equal to 98 newtons upward. The other information that you're given is that this is being pushed along at a constant velocity. So if it's being pushed at a constant velocity, and the force applied here is 10 newtons, what does that mean the frictional force must also be? Right. It's going constantly. Friction must be exactly equal and opposite to that. So this is what we know. We know the force of friction is 10 newtons. We know the normal force is 98 newtons. And we also figured out that mu should be equal to the force of friction divided by the normal force. 10, 98. Mu should be like right around 0.1. Sorry, I just realized I wrote a bunch without recording it. So just to re-explain, the weight of this thing is mg, right? It's mass times acceleration due to gravity. So you get 98 newtons for weight. There's no acceleration in the vertical plane, so the normal force must be 98 newtons. We know that it takes 10 newtons to push this along, and that it's moving at a constant velocity. So if 10 newtons to the right is being applied, and it's a constant velocity, that must mean F net in this direction is 0. So friction then must be applying a 10 Newton force opposite to that. Okay, so friction in this case is 10 newtons. We also sorted out just up here that mu should be equal to the ratio of force of friction to the normal force, and you get a mu value when you solve for this of 0.1, essentially 0.1. So the mu value between the table and this particular block is 0.1. No units. We need them to stay in newtons, so no units involved. And that's essentially how you would use this information to solve a problem with it. Okay, so the question you might be asking is, well, what is it that causes friction to begin with? So if I were to be able to magnify the surfaces here, right? So if I were able to blow this up to massive size and look at it, every surface, no matter how smooth it appears to be, is actually rough and kind of jagged on its bottom, right? Even some of the smoothest surfaces still have friction on them. Something like Teflon still has roughness, a little bit of roughness to its surface. Not much, mind you, but some, right? Okay, now, these surfaces can only really get so close together because they're made of different materials, right? And there'll be, at a certain point, a repulsion between those two surfaces. Actually, it's interesting because there's some attraction, actually. There's some electrostatic attraction between the two surfaces that might also contribute a little bit to friction. But beyond a certain, pressing down point, right? If you get them close enough together, they will start to repulse. But anyway, the point is, if this is stationary and this is being pushed, right? Let's say this is being pushed along, okay? If you notice, right, there's all these little lumps and bumps. So every time this moves forward, it's got to rise up and plop itself over the next bump, right? That's the first thing that has to happen. And if I were to push down on it, it would be more difficult to do that, right? So really the source of friction is the interaction between the imperfect surfaces of these two objects. And the reason why friction grows when the weight increases, or actually I should say when the normal force increases, is because the force between these two surfaces gets greater, or in other words, they're squashed together harder, and therefore friction will grow because of it. Are there any questions about that? Okay, let's solve one more problem here, just for fun. Let's say that we have this right here. And let's say that you were pulling this object. So I'm going to put some lines in place to help us understand this, because it's a little bit trickier maybe than what we've been doing. Okay, we're going to do this, this. Let's imagine that you're pulling some object, but you're not pulling it directly horizontally, okay? So let's say I tell you this. The frictional force on this object is, 40 newtons, okay? So let's say that FF is 40 newtons. And it's 40 newtons while you are applying a force over here. Okay? And let's say that the theta value here is 40 degrees. Okay, so you have this scenario. You are pulling up here. I'm going to draw you pulling. Well, you have super weird legs. Okay? So you're pulling upward in this direction. Okay? And I'm going to tell you this. This is an example. I'm going to say the object moves at a constant velocity. Find the pulling force on the block. Okay? How are you going to go about doing that? Well, one thing you have to realize is that this is at an angle, and therefore it has what we call components to it. Okay? In other words, part of this force is directed to the right, and part is directed upward. Okay, so if you look, we have a force at an angle, and so part of that force, right, is kind of like lifting upwards. We're not really interested in that, but we are interested in the amount of that force that's pulling to the right. So in other words, we take this force apart, we separate it into two other forces. So if this is moving at a constant velocity, what would we say this part right here is? And it has a name, actually. It's called the x component of the force. Oops, something's wrong here. Let's get rid of that. This. So we'll call this fx. What value does fx have to be? Yeah, it has to be equal to the friction, right? Friction acts in the horizontal plane. Therefore, this is moving at a constant velocity. The x component of this pulling force must be equal to that. Okay? If I know the x component is 40 newtons, and I know this is a 40-degree angle, can I solve for what this force must be? With trig. Yeah. So to solve this, we're going to say use trig to find the pulling force. Okay. So in this case, right, this is the hypotenuse. This is the adjacent angle. And you know from math class, right, that cosine of theta should be adjacent over hypotenuse. This is your SOHCAHTOA. And what we're actually interested in is figuring out the hypotenuse here. So you should get the hypotenuse, the force is equal to the adjacent divided by the cosine of 40 degrees. So to solve that value, we got 40 newtons divided by cos 40 degrees. We should get, so you get a value of 52.2 newtons. 52.2 newtons. There we go. Let's fix that. Okay, so you might see a problem like this down the road. So if you want to pull this, it's 52.2 newtons. Now, interestingly, this problem can be made a little bit more difficult if I just told you what the coefficient of friction was. The problem is, with that scenario, is you have to account for the fact that some of this force is lifting. So in grade 11, we don't often do problems where you have to consider that. So most of the time, you're just given what the frictional force is and asked to find this, which I think is fairly straightforward if you just keep this concept in mind. Next year, it'll be much tougher to solve a problem like that, because it'll be set up in a different way. But that's it.